Welcome to the presentation of CGO 2022 paper Aggregate Update Problem for Multi-Clock Dataflow Languages. My name is Kallwies. In this presentation, I will first introduce you to Dataflow languages in general and Tesla, the language we used in our paper. Then I will explain what the Aggregate Update Problem is about and show the implementation and the algorithm from our paper. In the end, I will discuss the evaluation results. Dataflow programming is a programming paradigm. The basic idea is that the data arrives on an input stream and successively an output stream is calculated. So a Dataflow program presents a stream transformation from input to output streams. Popular Dataflow languages are Lustre, Lucid or SRL, but also in the field of stream runtime verification, Dataflow languages play a role. For example, Lola, Striver and Tesla. To give you a closer insight how Dataflow languages work, I will present you our running example in the Dataflow language Tesla we use in the paper. On the left you can see a Tesla specification. It consists of 5 streams, the input stream I, and 4 other defined streams YL, Y, M and S. As we will see later, the streams YL, Y and S only have events if the input stream I also has an event. That's different for the stream M. M is defined as merge of Y and the empty set. The empty set is syntactic sugar for a stream that only contains one event with the empty set at timestamp 0. Merge merges together 2 streams, in this case Y and the empty set stream. So at timestamp 0, the stream M already has an event, the event with the empty set at timestamp 0. Now let's see what happens if an event on input stream I arrives. We now have to evaluate the remaining streams in the correct order. That means we first have to evaluate the streams that are then used in the other stream definitions. We start with stream YL. It is defined as last of M, I. This means always when an event on stream I arrives, we take the last value from the stream M. So in this case, we have an event on stream I, so we reproduce the event with the empty set on stream YL. Stream Y is then defined as lift of set add of YL and I. This means that the function set add is applied to the current values of the stream YL and I. As you can think, set add just adds a single element to a set. So what we have is we add 1 to the empty set and receive the set which only contains the number 1. Next we can evaluate stream M again. Now the empty set stream has no event anymore, but the stream Y has an event, so we just take it as event of the stream M. Finally we have the stream S. It's a lift stream again. It lifts the function contains to the sets or to the streams YL and I. So we check if the current event on stream I, the 1, is contained in the current set from stream YL, which is the empty set. So it's not contained. We generate an event with the value false. If we receive the next input event, for example 2, the same procedure is repeated. The event from stream M is reproduced, the set add is lifted, the stream is merged into stream M, and the stream S evaluates to false because 2 is not already contained in the set from the last timestamp where only 1 is contained. If we then get the next input event for 1, we basically do the same. We recover the event 1, 2 from stream M again and evaluate. This time stream S, for example, has the event true because the 1 was already contained in the set from stream M. So as you have seen, the basic idea is that we receive input events step by step and then evaluate the defined streams. Therefore, we have to take care of the correct order. So if you want to implement a Dataflow language, for example, translate it to assembly language or to another imperative language as we have done it in the paper, or just want to interpret it, you have to do the following. First, you construct the so-called dependency graph. In this graph, you have a node for every defined stream in your specification. And the edges between the nodes symbolize that there is a dependency. For example, you can see the dependency graph on the right side. There, the stream Y is dependent on stream YL. We first have to evaluate YL, then we can evaluate Y. You can see that also YL is dependent on stream M, but the line there is dashed. This is because it is not dependent on the current event of stream M, but on the last event. We don't have to take care of this dependency when we search the translation order. What we do then is finding a linear ordering of the graph such that we take care of all dependency edges. If you look at the right, the order from the top to the bottom is a valid translation order. We can choose that. Once we have this translation order, we just have to read the inputs and then in this order evaluate the streams. As you may have already recognized, these Dataflow languages have so-called immutable semantics. For example, if we take a look at stream Y, we add the function setAdd on the current event of YL. But in fact, we do not change the value of stream YL. We actually copy the event, the empty set, and then modify it to receive the new event of stream Y. However, the old event on stream YL remains unchanged, and is maybe even used again later when we evaluate stream S. So, if you think of implementing such a language again, you recognize that internally we have to make a full copy of the events if we take it in a lift of another stream. For example, if we calculate stream Y, we have to copy the data structure from stream YL and remain the old data structure. This is simply because we could need the old data structure later again. As you can see in Dataflow languages, the events don't have always simple data structures like ints or bools, but also complex ones like sets, here in this example. However, copying such data structures may be expensive and actually you want to avoid it. However, if you take a closer look at this example, you will recognize that the copying is actually not necessary here. Because if we evaluate stream S first and then evaluate stream Y, the old data structure, the old event of YL, is not used in the future again. So we could actually directly take the data structure, which represents the event of YL, and modify it in place to receive the new event of stream Y. However, this is not always possible, and sometimes, as in this example, it's a matter of the ordering or the translation order we have chosen. In general, this problem of finding the maximum number of data structures that can be modified in place internally is called aggregate update problem. It originates from the field of functional languages, but for Dataflow languages it's a bit different. The solutions there cannot be directly taken over. On the other hand, in both fields, as well as in the functional languages as in the Dataflow languages, the number of variables that can be modified in place is not solely dependent on the specification or the program itself, but also on the scheduling of the calculations. So what we have done in our paper is we presented an algorithm for finding the optimal translation order of a Dataflow program in Tesla, such that as many data structures as possible can be modified in place according to a criterion which we have developed. Then, when we saw that a data structure can be modified in place, in our implementation we used mutable data structures. If this is not the case, we used persistent ones. These are some kind of clever data structures which don't make it necessary to copy the whole old data structure if it is modified, but only the part that is modified and reference to the old data structure. In the following, I will present the algorithm from our paper in detail. First of all, we start with a classification of the edges. We take our usage graph again, and every edge there where complex data structures are passed are classified into the categories read, write, pass, and last. A read edge is an edge where there is just a read access to the original data structure. For example, stream S just applies a read access to the value of YL. So the edge between YL and S is a read edge. On the other hand, a write edge is one that really modifies the data type. So the edge from YL to Y is a write edge. Furthermore, we have pass edges, where the data is not modified, but just passed to another stream. For example, the merge just takes over the element from stream Y one-to-one. So the edge from Y to M is a pass edge, and the last edge is some kind of special pass edge, where the value is passed, but not during the current timestamp, but to the next timestamp. The second foundation of our algorithm is a notion of potentially aliasing variables. We say two streams, A and B, are potential aliases if we cannot prove them to be aliasing safe. That means it could be that the two streams carry the same event at the same timestamp. I will not present the details of this algorithm here due to timing constraints, but it can be found in the paper. But if we look at our example again, then we can see that the streams YL and M are not aliases, simply because YL takes always the last event of stream M. So M and YL cannot have the same event at the same timestamp. On the other hand, Y and M could have the same event at the same timestamp because M may just take over the event from stream Y, so they are potential aliases. Based on our edge classification and the notion of aliases, we have developed the criterion which variables may be implemented in a mutable way. Therefore, we have found three patterns, and a stream variable S may be implemented in a mutable way if it does not match any of these patterns. The first pattern on the left, double write reproduction, makes sure that a variable or a data structure is not written twice. A stream S may not be mutable if there is an alias stream S prime such that both streams are written or S prime is replicated while S is written. Because then we would modify the same data structure twice, or we would modify it before it is reused at a later timestamp. The second rule says if S is a mutable variable that is written, there may not be an alias which is read at a later timestamp in the schedule. And the third rule has to do more with our implementation than with the problem itself. It says if you have a variable S that is implemented in a mutable way, it may not be passed or transformed to a variable T that is not mutable. This is just to avoid expensive casts between mutable data structures and persistent data structures. Based on this criterion, I will now present to you the algorithm with which we find which variables may be implemented in a mutable way given the Tesla specification. The first step is that we determine the so-called variable families. These are sets of variables that can be, because of rule 3, which forbids castings between persistent and mutable data structures, can only be implemented fully in a mutable way or fully in a persistent way. In our running example, these are the streams empty set, YL, Y, and M. These variables either all have to be mutable or have to be persistent. In the next step, we search for all writes in our specification. In our specification here, there is only one write, stream YL is written. After that, we search for all aliases where the same data structure could be at the same timestamp. In this example, there is no alias for YL, so YL is the only node we have to take care about. Now we check rule 1 and rule 2 for this stream and its aliases. For checking rule 2, we see if stream YL is written only once or if there is another write or another last edge which originates from this node or from an alias. This is not the case here. It is only written once, so from rule 1 it still could be mutable. Then to check rule 2, we see if the node YL or any of its aliases is also read. This is the case here. Stream YL is written and read. Now we have to make sure that the read access, the evaluation of stream S, is done before the evaluation of stream Y. To ensure that, we add an additional edge to our graph from stream S to stream Y, a so-called read before write edge. Finally, when we have evaluated all write nodes, we then search a translation order for our graph such that as most blue edges as possible are cared. So in this case, we could, for example, find this translation order, then all standard dependencies and all read before write dependencies are cared, and so all variables in this graph or in this specification can be implemented in a mutable way. We have implemented our algorithm in the Tesla to Scala compiler and evaluated our approach. Therefore, we have written 3 syntactic examples, which are specifications that basically aggregate input events, quite similar to our running example. We did that for sets, maps, and for queues. We also had 3 variants of the specifications, one where the data structures only grow to a small size of 10 events up to a large size of 10,000 elements. In all cases, we could see quite significant speedups reaching from 1.48 to 4.97. Later on, we have also evaluated our approach for real-world examples, where we got similar speedups from 1.3 to 2.1. However, in one example, we even were only able to execute the specification with the optimization, because without the optimization, we ran out of RAM and our system started swapping, what caused the monitor not to finish. Now that we come to the end of this presentation, let me summarize the key points again. In the beginning, we saw how Dataflow languages can be evaluated by iteratively calculating stream events in the correct order. We then saw that in such an implementation, some of the updates of data structures can be done in place, while others cannot. The so-called aggregate update problem deals with the question how many data structures and which data structures can be updated in place. We developed a criterion to find out which streams in the implementation of a Dataflow language can be implemented with in-place updates, and showed an algorithm to find the perfect translation order to maximize the number of in-place updates. We have implemented our approach and the evaluation showed significant speedups. With this, I want to finish the presentation. Thank you for your attention. If you have further questions, don't hesitate to contact me.